Hello, everybody, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Riddell, and I will be your host this evening, or afternoon, or morning, of course, depending on the time zone which you live in. As you all may know, our goal is to have Python thrive within the National Lab System and associated research sites. And in support of that goal, we are joined today by our guest panelist, Jørgen, who is a senior research software engineer at Simula Research Laboratory in Oslo, Norway. His path into scientific software started during his PhD, where he used open source software in Python. In particular, he used FEniCS, a finite element software for solving partial differential equations. His initial minor contributions to the source code in user form gradually evolved into a more significant role as a core developer, forum administrator, and member of the FEniCS Steering Council. He's dedicated numerous hours to creating tutorials for FEniCS and associated packages, so we are very lucky to have him join us today. Now, before we go into our agenda and introduce our panelists for today, I wanted to remind everyone about a few key points for these exchanges. This call will be recorded, edited, and posted online. As a consequence, we ask that you all be conscious of the information in the questions that you may ask to ensure that you don't mistakenly or accidentally share anything that's privileged or requires clearance. Additionally, as you all know, we are a growing community and we would love to stay in touch with each and every one of you. If you would like to be kept up to date with our monthly exchanges, you can sign up for our mailing list, which you can find on our website, that's meetup.doepy.org. And additionally, on this website, you can find recordings of all of our past exchanges, as well as a recording of today's exchange once it has been edited and, of course, posted online. For those of you who have never joined us for an exchange before, I want to share with you that these events are typically broken down into 4 parts. First, we'll introduce our fantastic lineup of hosts and guest panelists so that you can get to know everyone here as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of academic and scientific research. Third, we'll turn things over to our guest panelist, Jørgen, who will share some prepared remarks on Python and FEniCS and how it fits into his life. And then to wrap up, we'll have a full discussion about the points brought up by Jørgen. And so for everyone out there in the audience, this will be your chance to ask questions and engage with our panel to help us all understand where Python fits into the life of research. Now, with that all being said, I would love to have the opportunity to go ahead and introduce our lineup of fantastic panelists for today. So I'll go ahead and share my screen. For our introductions, we like to play a little game called Ask Me About. And how we play this game is I'll go through each one of our panelists and I'll ask them, Cameron or James or Jørgen, what is it that you consider yourself an expert in? What types of questions do you want to hear from the audience today? So let's go ahead and introduce our host panelists with our game. Well, this one's a little bit of a cheat. I'll introduce myself. Hello, everyone. Again, my name is Cameron Riddell. And while I'm not affiliated with a specific national lab, I am affiliated with a company called Don't Use This Code. I would absolutely love to hear or address any questions that have anything to do with Python or any of the popular third-party packages, NumPy, Pandas, Matplotlib. I love to talk about Python. Any and all topics are valid for me. And I also should mention that I have a background in academic research where I study cognitive sciences, so finding the interplay there is always a lot of fun. But clearly anything Python is fair game for me. Let's move on to our next host panelist, James Powell. James, what is it that you consider yourself an expert in? And what types of questions would you love to hear from the audience today?
Hi, everybody. Typically, I say if you are interested in more community engagement, for example, with the SciPy conference series, the PyData conference series, or with NumFocus, the 501c3 nonprofit that fiscally sponsors one of the projects that we'll see today, please come talk to me. I'm very involved in all of these groups. But in fact, setting that aside, I have one topic of personal interest. If you are interested in APIs for tabular display of quantitative information, like tables with figures in them, I'd love to talk to you. I think I have an idea for a tool, totally incomprehensible, but will completely conquer the field of tabular display of quantitative information.
Awesome. Well, thank you so much, James. We are lucky to have you and your Python wisdom joining us today. Let's go ahead and ask Hiran. Hiran, I see that you are affiliated with Brookhaven National Laboratory, but Hiran, what is it that you consider yourself an expert in, and what types of questions would you love to hear today?
So I'm in NSLS2, the DSSI program, and I work on a lot of blue sky related technologies and blue sky tools, developing blue sky tools and stuff like that. I consider myself an expert in a very specific, relevant to today's talk, very specific technique called lattice-Boltzmann method, which is a hydrodynamic solver. So I was very curious about today's talk. I have actually touched FEniCS in the past a little bit as well. So I also have done a lot of GPU programming, and recently in the past 3, 4, 5 years, I've gotten into a lot of Python development in general. And I also have a background in quantitative finance as well. So I've done a lot of Python use cases there as well. So I would love to talk about anything in general, Python, and also using APIs and writing tools, sometimes client tools very efficiently to access like third-party APIs and also developing APIs. So that's it.
Awesome. Well, Hiran, it sounds like you are the triple threat with Python, math, and even FEniCS specific knowledge here. So Hiran, we'll definitely be relying on a lot of you to help out with our questions and address anything that our audience has to ask. So thank you so much for joining us today, Hiran. Next up, we're also joined by Dan Allen. Now, Dan, I see that you're also affiliated with BNL, but Dan, what is it that you specifically consider yourself an expert in? What types of questions would you love to hear today?
Sure. Lately, I've been thinking a lot about the different scientific data structures and containers for numbers that we have in Python, when to use a NumPy array versus the different new kinds of data frames versus something more exotic like sparse or my new favorite awkward array or even ragged array. So thinking about different tools that we have and when they work. And my usual answer here is building ground up informal collaborations across the labs. Always happy to talk about that.
Fantastic. Well, I believe we'll be talking a little bit about some arrays today, so we'll definitely want to hear your knowledge and your thoughts on that. And I'm very glad to have you join us because spreading Python at the DOE affiliated labs is exactly what we're here to do. So thanks so much for joining us today, Dan. Next up, we'll introduce our guest panelists. Our guest panelist today is Jørgen, as I mentioned earlier. And Jørgen, I'm very curious, what is it that you consider yourself an expert in, and what types of questions would you love to hear from the audience today?
Of course, I do consider myself an expert in FEniCS, as I spent a healthy amount of time using it. But I also dedicate quite a lot of time to work on reproducible examples and also like pipelines, CI, and diving into libraries to like find the smallest minimal reproducible example and then make issues at the relevant GitHub repository. So that's something I would love to help people with, is just, do you have a big problem? We can probably dive into it and get it down to 10 lines and make an issue or a pull request to any relevant repo.
I love to hear you mention the reproducible examples. Jørgen, something I didn't share is that I know both myself and Dan Allen have a considerable number of points on Stack Overflow. And the best questions are the ones that have just a small copy-paste reproducible example. It just makes things so much easier. So I'm glad to hear that you're doing that for your issues on GitHub so you can simplify your developer workflow. But Jørgen, it is a pleasure to have you join us today. And that wraps up our introduction of all of our panelists. I also want to mention to everyone in our audience, you too can become a host panelist. All you have to do is reach out to our team at doepy@dutc.io and just let us know that you're interested. We'd love to have your expertise and have you join us up here. Now, with our introductions wrapped up, why don't we jump into the next item on our agenda? That is our coding activity. And today's coding activity is a very fun one. It's called The World Does or Does Not Need Another. And the premise goes like this. We'll present some tool within a confined technology space. Our panelists will provide guidance on how crowded that space is already and whether or not we actually need a replacement tool. Then the panelists will be scored, not actually, on the specificness of their response with bonus points for relatable anecdotes and experiences working with scientific researchers. So let's go ahead and we'll jump into our very first question for our coding activity. And this one is, I need to run computationally intensive code from Python. So I created an array-like object that has a .sum. It even provides an access interface within multiple methods. I created an array-like object to quickly calculate descriptive statistics. Does the world really need another NumPy or Pandas replacement? So I'll open this up to our host panelists to see who has some thoughts on this.
I don't want to yet weigh in on whether we need another one or not, because obviously there's an answer there, but it can be a little bit controversial. But I will note that at one point in time, I went to bed hearing people say, MATLAB is never going to go away. That's the end of it. They solved all the problems. This field is done. And I woke up the next morning and everybody was talking about NumPy and Python. And I might remind everybody how quickly all of these things can change and how readily what we assume to be a done, finished, set in stone can be upturned by a new upcoming upstart project.
I guess I'll jump in and say the important thing is to not break the nice interoperability that we have, the ability to combine the tools in ways not foreseen by the people who created them, to pass my image to a machine learning algorithm to a plotting tool that didn't have to explicitly coordinate. So when people come up with reasons for new array-like objects, I hope that they're reading the array API and making it so that their arrays and my arrays play as nice together as they can.
Am I going to get in trouble if I say that I think some of the API unification work is actually not particularly useful for anybody?
Expand on that. I disagree.
Starting from the data frame perspective, I think the data frame unification stuff is...
data frame perspective.
Yeah, that's absolutely useless. Complete waste of time.
Yeah.
API unification, I think, is a smaller version of that, whereby does it really matter that much if I call it .mean versus .average? People will write their shim layers anyway. And are the tools really that similar that people don't want the specifics? The anecdote to recall is, I remember at one point in my life, everybody said, oh, never interact with your database directly. Always have a layer in between, because one day you'll decide you don't want to use MySQL anymore. You want to use Postgres. That never actually ever happened. And only for maybe library authors of core projects did they want to have that breadth. For everybody else, they start with a tool and you never really do anything with your intermediary layer to move off of that, because the tools are just fundamentally very different in the end. QPy is quite different than NumPy.
I've written code that works on NumPy or Dask, and I've done it with array function, which was pretty confusing. And I've looked at what it would take to do it with array API, and I think that's significantly, if not massively, better.
So just to jump in with a slightly different viewpoint, is like, for instance, I feel like NumPy as n-dimensional arrays, it's a library I use a lot and I really like it. But there are things there that I hope will get better over time, that I think there is room for improvement. And I see other libraries that also wrap NumPy objects. So they do not necessarily make NumPy objects, but they have wrappers to become NumPy objects that have solved some of these issues. So there are exciting tools out there also for more like data frames. There are tools that can solve the problems that you have or make your life a bit easier with, say, type hints, or just like not accessing the whole data frame every time you want to do something, that you do more of a graph kind of filter that you can apply that certain libraries do, which I think is really exciting.
Dan, you're basically with Blue Sky telling a bunch of people, here's a better way to do things, and it may require that you rewrite a bunch of stuff you'd already written. Is it really that much of a pain to tell people, go rewrite all of your stuff? It seems to be the case that we do this often enough in practice, and people hate it, but they kind of just do it. Or for our colleagues from Livermore, it's Yorick all day long until one day Yorick no more, and then rewrite all your stuff. Yeah, it's not great. Everybody hates it, but it's just kind of a fact of life, isn't it?
Yeah, I think these are two different categories of thing, though. If tools are really solving different categories of problems, like DuckDB versus Pandas, those are very different tools. Or, array libraries that are doing something substantially different than NumPy, interested in a different category of problems. Then, if you thought you needed one tool and then you realize you need a different tool, you're rewriting your code, and that's fine. There is this garden of very similar tools in JAX, CuPy, NumPy, and Dask that are close for many reasons. And I think there's value in making them the same where there's no good reason that they should be different. It's not that hard. So seems worth it.
Fair point. And I think if you're developing something that sits on top of another technology, like Jørgen was saying, right? Just make sure you're using it efficiently and don't reinvent the wheel if you don't have to. And I think from the perspective of the example we've written here, if you're doing a project, right, and you need to compute an analysis and come to a result, I don't think you need to go through all the hoops of creating your very own array library, unless you're dealing with data that simply NumPy does not work well with. And I would always encourage you to reach out to see if there's an existing tool that covers your use case before you go and invent a wheel, because making an array library, making one well, is not easy at all.
There's one thing we can all agree on, and that is that making a new array library is probably more fun than whatever the original problem was.
That's the thing that's the aspect of your work you'll enjoy, but not the one that you'll get funding for. All right. I think we've wrapped up round one here. Why don't we move on to round two? This one's a pretty hot one, probably the last 12 months or so. I'm unsatisfied with Python's package management, and you know what? I have the solution. Well, I created a new one because I can do it better. So does the world really need another Python package or environment manager?
I'll just say there's a relevant XKCD for that.
Yeah, there's 15 competing standards, right, Aaron?
Yeah.
Huron, my understanding from your colleague Tom is that the answer is no, as long as we just stop using pip and wheels. Is that about right? Is that accurate?
Yeah. Well, I would say like drop-in replacements for some existing package management systems with improved performance, like Mamba and UV and that kind of stuff. I really like. As long as you can just use them just exactly the same way you use the other tools.
I think we probably should have another package managing system, but getting people to use it is going to be the problem. So first, getting all the developers on board, saying, okay, you need to change your specification of how you want to install this, or put it in, say, Conda Forge, or put it on Spec, or put it wherever. And then you need all the users to actually use it and test it. And I think that is going to be a very slow process, because people are quite conservative when it comes to how to install their libraries. So I think it's a challenging task, but I hope it will happen.
I'm suspicious of any effort like this that thinks all the existing ones are making it too complicated. And there are some in that category, but UV and Mamba, like Karan said, are not in that group. I think people approaching this with humility and empathy probably will find opportunities to do better than we have so far.
Yeah. I found that a lot of the problem here comes down to all the data scientists, right, also want to wrap up their C, C++, Fortran, whatever it might be, into the Python code, right? And then pip will just bundle that as a wheel. And that becomes, right, an issue down the line if you're depending on other C or C++ libraries, things like OpenBlast, right? This is only an issue for us data folk, right, who need these heavy computational packages. It's not as so much of an issue for folk who build a Django project and don't have to do any heavy array-like computation. And so the community ends up getting a little divided and saying, why would I ever use Conda? That's so heavyweight. Pip does everything I need it to and does it flawlessly. And then you ask them, well, do you need to reproduce on a different version of Python? And then they either know how to install Python or they don't. And so, that's part of the issue that I see is some people are completely happy with the tool that exists and they don't see any need for it. And other people, like ourselves or Jørgen, right, you might encounter on a daily basis of, oh, well, I need to go run some code on Python 3.4 and then I need to install these packages, but I also need to keep the version of OpenBlast that I have on my computer and not have anything vendored sit on top of it. And so that's where a tool like Conda might be helpful. So Jørgen, I agree with you, right? It's partly a big social problem of getting users to adopt a specific tool and then to use it how it was intended to.
I think also, since you mentioned the heavy computational cost, where you need, say, OpenBlast or you need some other C libraries to actually do the heavy lifting, then you might need an HPC system, and then you might want to optimize everything for your compilers, and there Conda doesn't always fit. You can't always squeeze the best performance out of Conda there, and you can't use Docker on HPC systems. You can maybe use it to Singularity, and it works quite well most of the time, but sometimes it doesn't work. Could be your MPI compiler or something similar that doesn't fit, and then that's where I'm at, where I think like there are other solutions out there that are exciting that could solve these problems. They're not perfect either because they might take. So one of the tools that I think about is SPAC, which installs everything from scratch. So it takes ages, but you're going to get the most optimized version, and you only need to do it hopefully once a week or so if you work on the bleeding edge of packages. But it's not like Conda or Mamba where you can get your resolution in, say, a minute if you don't have too many complex packages.
What about stuff like Napari, which are desktop apps that have some plugin infrastructure and they're used by just regular users, and you're writing a plugin for that you want them to install? Do you really need them to drop down to the console and Conda install some plugin? Or does it make sense for those tools to have their own package manager so they can have a one-click graphical embedded mechanism?
I think in the day of now, where we have apps and everyone is used to apps, probably it would be suitable to have a graphical user interface where you could just say, I want to install this package and drag and drop. And then you would maybe get like an error message saying you get some conflict resolution. It's not something that I would use myself, but I see why people would find it like comfortable, because that's the interface they see on their computers or phones or iPads or tablets every day.
Very fair. And Jørgen, I'm glad that you mentioned SPAC. We actually had Todd Gamblin join us about a year and a half ago, talking about sustaining the HPC software ecosystem with SPAC. So glad to hear that little cross-pollination of the tools there. All right, why don't we move on to our third round here and what will be our final round. We've seen a lot of these tools usually on social media, I'm sure, but do we need another auto UI creator for GUIs or TUIs? And the reason is, I create so many simple GUIs. So I create a tool that simplifies the process of making some broad assumptions by making some broad assumptions. Does the world really need another auto UI creator for these things?
I think I think it was James that mentioned it earlier, that you don't know, like suddenly someone figures out some completely new use case that you haven't seen, and it makes life a lot easier. So we don't know. I think maybe, like, I personally use GUIs as little as possible, but I see how powerful they are for end users. And if you want to convey a message, making something a powerful statement saying this is a very useful tool that's easy to use for people that don't do coding. So suddenly someone figures out a new fantastic way of simplifying the process, and people latch on, and then it's going to be popular. And I think that could still happen.
I think for me, this is the category where there's the strongest case for having a huge number of these, because I think the limitation that they have is that it's very hard to make a general purpose one. So that leads you to the conclusion that you need about as many of these as there are people, or at least groups of people doing similar things, and the definition of similar being pretty tight.
Very fair. Dan, do you make GUIs very often?
No, I used to do a lot with IPy widgets, so I'm familiar with the space.
Okay,
but
and so you would just
recently,
keep them
no.
in a notebook, right? So then you could just live by your code. Very fair. Well, I was sharing this a little earlier, but for our audience, I make GUIs not incredibly regularly, but when I do make GUIs, I always end up reaching for the lower level tools, something as straightforward as tkinter, right? And that's just because I know I can get an MVP out fairly quickly, and I'm sure with an auto creator, you can get an MVP out extremely quickly. But then when it comes, a week down, 2 weeks down, and like Jørgen was saying, somebody asks you for that specific, additional feature, or you have another use case in mind. If you're using some type of auto creator, if you don't have the escape hatches in the right place, you might just find yourself against a wall where you have to go back and just go for the lower level tool. And so I often reach for the lower level tool to begin with. This is also my justification for starting all my data visualization projects with matplotlib instead of going through Seaborn as a first pass.
Something that occurs to me, though, is that, Karen, correct me if I'm wrong, I think you're probably receiving requirements from someone else who knows what they want. And I think that the auto GUI creation tools are mostly for single user projects where the person coding is setting the requirements and is willing to be a little flexible about those requirements based on how quickly they can get the tool to do what they want.
I agree with you there, Dan. For my projects, I wish the clients would tell me what they wanted. Oftentimes they don't know the specifics of what they want.
Yeah.
And so, but at the same time, I know that at some point in the future, I need flexibility. So I guess if you start off with that mindset, just go with the lower level tool. But if you know all you need is just a really quick thing, you're going to do it as a one-off project and just keep reusing it the exact same way and never expand. I think there is a space for these auto UI creators. I don't know if the world needs another one because there's already a good number of them out there. But I think that's a good differentiating point as to I'm starting a new project. Should I use an auto creator or should I just go for a lower level toolkit? So thanks for bringing that up, Dan.
I'm playing devil's advocate. Obviously, I do not use these, but it's interesting to think about. It depends on who you are and where you're sitting.
Absolutely. All right. Well, if there's no other thoughts here, we can conclude our third round. And with that conclusion, Jørgen, I'm going to turn things over to you.
Today, I will talk about the tool that I use most of my time on, which is FEniCS. And I'll first start with some information about me. So some of this has already been covered, so it will be quite brief. So my introduction into programming at all started with Python in 2011 at the first year at university. where I had a course on scientific computing with Python by Hans-Petter Langtangen, and where he used his book, A Primer on Scientific Programming with Python. And then I really loved that course. I really got into Python. But then that course ended, and I did a maths degree, so I diverged into other tools like R and MATLAB. And then I was reintroduced in another course by Hans-Petter to FEniCS in 2014. But for my master's degree, I actually ended up using Fortran 77 because I did something completely different. So there is a 2-year delay before I started the PhD, and I started actually using FEniCS for anything. So during my PhD, I used FEniCS to solve shape optimization problems. And then in 2019, I started contributing properly to the FEniCS forum. I started a postdoc at the Department of Engineering in Cambridge. Then once that was done, I moved back to Simula in Norway, and I became a research engineer. At the same time, I became part of the FEniCS Steering Council, and I'm currently now a senior research engineer. So with that, I do a lot of programming, but I do programming for a lot of different projects, not just FEniCS, but FEniCS is my passion. So before we go into FEniCS, we should talk a bit about the finite element method. So the finite element method, or the foundations for the finite element methods, which is mathematics, started around 1909, 1910, 1915, with Ritz, Rayleigh, and Galerkin, thinking about, okay, we have a partial differential equation, the PDE, which we can see on the right here. We have the residual of a partial differential equation, the Poisson equation. And they thought about, okay, what if we use a finite dimensional space to represent these with some basis functions? We want to find the coefficients ui in this sum here, UH. We want to find the approximate UH in some function space with some basis functions. And they would use some global basis functions, and they would say, okay, I want to test the residual against every basis functions from this space. So this was a mathematical method that was used with like one basis for your whole domain. And then it took 30 years, and people started thinking, maybe we could subdivide our domains into triangles. And with subdividing domains into triangles, you end up with a finite dimensional set of basis functions for each element, and that's where the finite element method was born. So in the 1940s, the development of finite element code started, and already in 1958, the first finite element open source software was created at UC Berkeley. It was a Fortran code, it was distributed, and people could use it to solve structural mechanical problems. Then there was a lot of software development from the 50s to the 70s. And in the 70s, a lot of general purpose finite element software started appearing. So you had finite element software for structure mechanics, but people also started looking at how can you do finite elements for fluid simulations. And with that, a lot of mathematicians started looking at this finite element method, and started proving a lot of important theorems for stability of these of Galerkin methods, and how you can formulate a PDE to solve certain problems and what boundary conditions you can have. Then in the 1990s, object-oriented programming took over a lot of these finite element codes, so you end up with deep hierarchies of functions inheriting from each other, and there were so many finite element softwares, and there are so many that are still around that use this kind of frame. Then in the 2000s, people started looking at Python and thinking, I want something user-friendly. I want to have users that can easily interact with my tools, because Python is a very beautiful and simple language. But in 2010-ish, probably even before that, but most people didn't really think about high-performance computing as in like looking at billions of elements in your domains before 2010. So with that, the user-friendliness of Python could become a bit challenging. Because if you have something that's very user-friendly, you can make people do things in a way they think is efficient. It's efficient up to a certain point. So then we'll go into the history of the FEniCS Finite Element project. So that started all the way back in 2002 as a C++ library, a library called Dolphin. And then in 2003, multiple universities and researchers sat together and created the FEniCS project that then encapsulated the C++ library Dolphin. Then in 2004, the FEniCS project started using code generation. So instead of writing all the code that you need by hand for solving finite element problems, they figured, why not generate this code? And we will talk a lot about this throughout today's talk. Then in 2005, which I think is relatively early, the first Python interface for Dolphin was created, called PyDolphin. Then in 2009, people started thinking about parallel support, so supporting MPI and distributed computing systems. And the unified form language is a cornerstone of the FEniCS project, was introduced. From 2016, we've been sponsored by NumFocus, which makes our life easier. We have a strict code of conduct, and it makes the software sustainable. And with the change for doing things with MPI, we saw a need for rewriting a lot of the initial code that was created from 2002 and onwards. So from 2017, and it's still under development, the last release of a version was 2 hours ago. We developed something called DolphinX, which is our next generation finite element tool, and that's the tool I'll talk about today. Some statistics: we have about 3,000 users on our discourse forum and 12,000 monthly downloads. So compared to more core libraries like Pandas and NumPy, we can't compare, but we're quite big in the specific space of finite elements. So if you're, after this talk, you're interested in learning more about FEniCS, I have an online tutorial on my webpage, which was shown at the beginning, where you can find interactive tutorials. So we could go to a tutorial and see, do you want to see how we can solve a deflection of a membrane problem? It walks you through the mathematics, and you can go down and look at beautiful plots of deformation and pressure and deflections. And I have a wide range of examples here. Some of them I've included in this presentation, some I have not. Here are some other examples that you can find. So you can find hyperelastic beams or fluid flow using splitting schemes for known fluid benchmarks. So let's start at the beginning. So in the beginning of this talk, I talked about the Poisson problem, which is solving the Laplace of U equal, the Laplace operator of U is equal to 0, or the Laplace operator of U is equal to F. So to use DolphinX, the first thing you need to do is to import MPI, because we want to work in a distributed system. So we're going to import MPI, we're going to import the core library DolphinX, and we want to use PETSI to solve our linear problems that are going to arise from setting up a finite element discretization. So we import the submodule PETSI from our library. We import the unified form language, and we import NumPy because we like interacting with other libraries. So we start by creating a unit square mesh. So you can see this slightly extruded mesh over here, which has the solution of the problem that we're solving. So you want to make a 3x3 mesh, and you want to distribute this mesh over all available processors by saying we want to use MPI convolve. Next, we want to create the function space where our unknown is going to live in. So we're going to choose fifth order polynomials from Lagrange space. And we're going to talk more in detail about these kind of spaces later. We then use the unified form language to specify our variational form. So if you know the finite element method, the idea is you take the Poisson equation, which had the Laplace operator, you multiply by a test function v, usually from the same space, and you integrate by parts. So then by integrating by parts, you get a gradient on U and a gradient on V. Say we want to have some varying source f that depends on the x and y coordinates in our grid. We create a symbolic object using UFL spatial coordinates, and we create our f and our l's. Now we have our bilinear form and a linear form, and we would like to solve the equation A equal L. And before we do that, we want to say something about the boundary conditions. So in this example, we're going to clamp all the boundaries where x is equal to 0 and x is equal to 1. And we do this by using the modern Python lambda functions and numpy. So we create a lambda function here that takes in an n-dimensional numpy array. We're going to check when the x-coordinate is equal to 0 or the x-coordinate is equal to 1. And we send this in together with our function space, and it locates all the DOFs, or the degrees of freedom, the dots you can see in this plot, that satisfies this specific condition. We say that we want to fix this to 0, so we create a symbolic constant, and we use PETSI to say we want to create a linear problem with PETSI. We want to use a direct solver, so an LU solver, and we say solve, and we can store this to VTX or VTK or XDMF, and we can write this to file and visualize this in ParaView, or we can extract the solution directly in the Python code and use PyVista to visualize this interactively, as you saw in the previous slides. So this is the idea of FEniCS. So you have some symbolic language describing the mathematics. You just define your boundary conditions, and you interface usually with PETSI for solving the linear problem. But how does this actually work? So FEniCS is quite a big package, and we've already looked at some of the evolution through the historical nodes on FEniCS. And at the core of FEniCS project, we have UFL, which is the form language we use, which is a domain-specific language to describe finite element forms. And we're going to go into quite some detail on what that means. But we also need to say something about the finite element functions we want to use, and that's where we use BASICS, which is a C++ library with a Python interface, where you can tabulate or compute basis functions and arbitrary order derivatives of basis functions for a large variety of spaces. Then we have our form compiler that generates code using UFL and BASICS. So using these two, this symbolic language and this basis function evaluation library, it generates C code. And then on top of this, we have a Python module called DolphinX that has a lot of different sub-packages to handle various tasks. So you will see some of these today. You've already seen DolphinX PETSI. You will not see all of these today because we simply don't have time to cover all of them. So we'll start with BASICS. So BASICS is a tabulation library. It has a nice web page with a lot of documentation and a lot of demos also for how to do this in C++. But we'll go through some of the features today. So what I mean by tabulating is saying, okay, I have some polynomial function, my basis function. I want to evaluate this at some points on an element. And this is a task that you could think we could just have a symbolic library to do this, but this becomes incredibly slow if you want something else than first-order functions. Then BASICS also provide you quadrature schemes that you would use for your numerical integration. So both of these are in the core of BASICS. It's, as I said, written in C++ with a Python interface. It can do these tabulations then at runtime compared to the old FEniCS, where you would generate code to evaluate basis functions, which could be quite costly. And if you're in the experimental mood, you can create your own finite element. So if you're a mathematician and you want to experiment with your finite element, you can put in a formal definition by reading through documentation of what the formal definition of finite element is. And you can use that with BASICS and then directly in FEniCS. So one of the nice things with BASICS is it yields extra control over how you want to define your function spaces. So here we're again going to look at Lagrange polynomials. That's going to be a 10th order polynomial we're going to try to approximate. And the key with the finite element method is that every node in this cell here is going to have a function associated with it. And it's going to be one at the node it's associated with and 0 everywhere else. So by moving these nodes slightly, as we can see in this rightmost image, where we have more nodes closer to the corners, you would get slightly different polynomials. And these are two different variants of finite elements. And you can say, why? Why do you need this? And you can quite easily see this if you want to approximate this sawtooth function here on the right. You want to do this, and we can write code for this quite easily in FEniCS. So here we have a simple code that creates this sawtooth function. That's the first code here. It just takes in the core x, y set vector, and it creates this sawtooth function that you see on the right. We now want to approximate this with a finite element space of a given variant on a given grid. So we create a unit square of quadrilateral elements. We create our basis functions. We can create the function space, and then we just want to interpolate this sawtooth function into this function space. So that's what this lambda function here does. It takes in all the DOF coordinates of every cell in your mesh, and it evaluates at the DOF coordinates and populates the function UH. We can then compare to the exact solution by creating a symbolic expression that will be evaluated at poetry points, and we can look at the error. So if you look at the error for these two, you see that the equispaced approximation, which is the approximation most people see, you get a way poorer estimate when you reduce the mesh size. So you see that there's an order of magnitude difference in convergence here, where you just want to approximate a simple sawtooth function that is definitely within a 10th order polynomial. And this phenomenon is called Runge's phenomenon. And it's something that most people don't think about, but we give people the opportunity to experiment with these kind of things. So that's one of the reasons why FEniCS is quite popular. It's really easy to experiment with different variants of finite elements, variants of variational forms. The next thing I want to talk about is the form compiler. And to talk about the form compiler, I also need to talk about the unified form language. So at least some of you might have heard about the mass matrix, which is just taking the inner product of two functions u and v, where you represent each with a set of basis functions. And if you want to create a mass matrix in Dolphin, you could just do it by importing UFL and creating your element with the basics UFL wrapper. So here we're creating first a symbolic representation of any mesh. So this doesn't need to be the actual mesh you're solving on. This is just a symbolic representation that says you're going to have first order triangles. That means triangle with flat edges, and it's going to be in 2 dimensions. We create the finite element that we want to represent our functions in. It's going to be on triangles. It's going to be third order. So it's going to have third order polynomials. The mesh doesn't have third order polynomials, but that's absolutely fine. And we create the symbolic expression here. A is inner UV dx. And what we want to do now is to be able to create a numerical representation of this, a matrix, a sparse matrix. We'd like to generate code to create this for any element you send us. So by calling FFCX on this, what FFCX does is it uses UFL to create a graph of operations of what you need to do. So when you have the inner product here, inner UV dx, that is on any triangle. And if it's on any triangle, we want to map that back to the reference element. So if you map that back to a reference element, with standard calculus, you need to add the determinant of the Jacobian to your integral over the reference element. So that is the whole computational graph you see here on the right. You see that you want to get the absolute value of the determinant of the Jacobian. And you also see that you multiply 2 reference values. One is the trial function, one is the test function. And by having this symbolical expression in a direct acyclic graph, we can now generate instructions on how can we compute these from a given subset of information. So let's generate some C code where you say, I want to fill in a tensor A, where I have some known finite element functions W and some constants for any element in physical space described by some coordinate DOFs. We're going to ignore the last two entries here today, so you don't need to think about them. And then we want to generate the full assembly of this for any element in space. So first we need to know, okay, what quadrature rule are we using? That's determined by a UFL or FFCX if you specify a given quadrature rule. So then you get the quadrature rule. Basics evaluates the finite element functions and its derivatives at the quadrature points, and that's where you get these static tables. The next thing you get is that you generate the computation for the absolute value of the Jacobian. You then generate the local population of a tensor. So we're not going to go through this code because any user will never see this code because it's generated code, so it's never something a user actually has to interact with, and that makes life quite easy. So some features of the language is that we can do single, double precision. There is experimental features for doing half precision as well. We can do real and complex valued tensors. We can assemble into arbitrary order tensors, so you don't just need to do a scalar value, a vector, a matrix. You could do a four-dimensional tensor. It just becomes incredibly computationally expensive to store. You can do curved cells, and you can do discontinuous elements for any element we support, and the elements we support are listed here in this list. So we support quite a wide range of elements. So how does this actually work when you would like to write your code? So we saw in the first example, the Poisson example, that you didn't see any C code, you didn't see any compilation of C code. And what happens is, under the hood, if we want to just create the mass matrix on a unit cube, we create the symbolic representation here for A, and under the hood, dolphin_x, when you send it into the linear problem, we'll call dolphin_x fem form. This is going to just in time compile this symbolic representation into a C function. And we're using the C foreign function interface for this. So then we get a C function that we could pass down to C++, or we could just evaluate it in Python. So it's quite a nice thing to be able to create C functions that you can use directly in Python, or you could send them to C++ if you want to just work in C++. We also want to make the library not just an ecosystem or a language. We want to interact with all the other great libraries that are out there. So instead of having a deep object-oriented design, we use a functional design where we send in data, usually NumPy arrays when you work in Python. So if we want to create, say, a mesh with two quadrilateral elements, we say, okay, these are the nodes in our quadrilateral element. They're numbered 0, 1, 2, 3, 4, 5. And then we say the cells, they are numbered with the vertices 0, 1, 3, 4, and 1, 2, 4, 5. We can then send that into the create mesh function in dolphin_x, and this will generate the mesh you want. And here we're using the self-communicator. So if you run this in parallel, you will get one mesh on every process. So that could be neat if you want to do many small simulations with a wide range of parameters. But of course, we also want this to work with MPI. So that's what we're going to cover in the next slide. And at the bottom here is just a reference of something unique that we do in dolphin_x that I'm not going to cover today. So we can create meshes in parallel. You could distribute your data on every process. So here we just have a check on which rank you're on with MPI. You can put some data on one process, some on the other, nothing on the others, and then we can send that to our mesh creator, and that takes care of all the data handling. So you can work directly, nicely with the known structures from Python. And we use nanobind to bind from C++ to Python. And nanobind has a very nice way of moving multidimensional arrays without copying using std span. So we do not copy data when we move data from Python to C++, except if we really want to copy the data. We have a very specific ownership structure for any mesh element. So when you send this to the mesh creator, this gets partitioned by your favorite partitioning algorithm. You can also choose to partition it yourself if you want to. And then you get these kind of ownership plots for every process. And you would also have these index maps, as we call them. You can read more about that in the DolphinX paper that describes very minimal structure for saying, I have some distributed data with over M number of processes, and certain data shared with a subset of other processes. We also love to work with other libraries such as Numba. So what if you don't want to use UFL, you don't like code generation? We could create your own kernel. So that's what we're going to see quickly in this example. We could use Numba to say, I take in a pointer to the matrix A. I take in some known functions, some known constants. I take in the coordinates. And I just want to make my own mask matrix based off the coordinates of the elements. So here we take the coordinates of the cell, and we compute the determinant of the Jacobian, and we use some pre-computed mask matrix that you could use basics for, or you could compute it yourself if you want to. And then we can easily interface with DolphinX. So you can send this into DolphinX, then you can use this with an MPI distributed system. So if you want to write your own matrices, you could do that. But what if you want to do something even weirder? So you want to do a custom operation on a local tensor created from DolphinX. You could do that by using Numba. So you can use the C kernels we have. You can call that populate the local matrix, and then you could do some custom operation on that, for instance, mask lumping, which this example shows. So now I've gone quite quickly through the last examples. We have tons of demos. I have tons of tutorials online. And if you have any questions, we will take them after the talk. But I'm also on the FEniCS forum every day if you have any other questions. So the final thing I want to say is that we're doing the FEniCS 2024 conference at Simula in Norway from the 12th to 14th of June. There will be 48 talks and a poster session. So if you want to learn more about FEniCS and all the crazy applications that it's used for, please attend. So that's all I wanted to say today.
Fantastic. Thank you so much, Jørgen. Let's go ahead and we will open the floor to questions. We have a few minutes left here, and so we'll probably get to 1 or 2 questions. But if you're in the audience watching and want your question answered, please go ahead and use the Q&A widget. And while we're waiting for some questions to pour in from the audience, I would also like to open it up to our floor of host panelists and see Dan, James, Hiran, what questions do you have for Jørgen?
I nominate Hiran as expert.
I've used a finite volume method and then moved on to a lattice postman method, which are like completely different methods. So I wouldn't say I'm an expert in finite element per se. But I want to ask one quick question about that. The reason why I moved on from finite element to finite volume was at least at that time, my understanding was that the conservation laws are kind of like difficult to pin down with finite element. So that was the reason why I moved on to I moved on to OpenFOAM first. I don't know if you're familiar with that. Like, could you kind of compare the two, not from the finite element versus finite volume, but basically their software architecture and how they work? Is that similar or a different approach?
I would say quite different. It's been almost 10 years since I used OpenFOAM, but the idea of FEniCS is that you generate code for every kernel. So if you can write your mathematical expression in a variational form, we can generate code for it. So then you can experiment with a lot more than you can in these libraries where you need to implement your own subroutines if you want to do something very specific that is not part of like the common plugins. So we don't provide a specific set of equations you can solve. We say if you can write it, we can give you the matrices that you need and the interface to an appropriate solver. So it has quite a different take on how to solve PDEs.
Thank you.
You mentioned nanobind. I've heard that all the cool kids are using nanobind now. Do you have your sense from your perspective on where that is in its development life cycle? Should I forget about PyBind 11?
Wait until the 2.0 release, because there are some major things coming up there on the typing from the Python side. which I think will be very useful. So it's not there is not a formal release date, but it's way faster. It's remarkable how fast it is, and there is very little change from how you use PyBind. So shout out to Nanobind. It's a great tool. It does everything we want it to do, and it just is way faster. So it is really neat. But wait until there's going to be a major change with the typing. So I would wait till that's done. And depending on how, I hope that happens within a few months. But also it's going to be very good if you are on very modern Python, then it's going to use the stable API. So it's going to be less surprises in the future.
Fantastic. Well, thank you so much. We have not received any questions in the chat. So Dan, yours was the last ringer that we have time for, since we are now out of time. But this has been such a wonderful Python exchange, and I want to extend a huge thank you to Jørgen for taking the time to join us in my time this evening. And I also want to thank our audience for joining us this month. Now, if you are not already signed up for our newsletter, please do make sure that you subscribe. The subscription link can be found on our Meetup website. That's meetup.doepy.org. Or if you don't like receiving just one email a month, well, keep a regular eye on that website for information about our upcoming exchange next month. Thank you all again for joining, and I hope to see you all next time.